temperature of this is reducing 5 degrees centigrade per hour. Huh? Okay. So suppose it's inside a container or in a fluid which has very low thermal conductivity and very low heat transfer coefficient. So that kind of system we kept this copper ball.
Yes, sir.
So because heat is removing very slowly, so it has enough time to eliminate any gradient inside the sphere.
Okay.
So suppose it has taken some small amount of heat. So there will be a small temperature gradient established here. Say it has just 400. So initially everywhere inside this ball is 400. Initially 400, 400. Now in 1 hour or say in 5 minutes, you remove such a heat that it becomes 390 degrees centigrade. But immediately it will take, because its thermal conductivity is very high, this temperature gradient 10 degrees centigrade is eliminated in a matter of 1 second.
Okay, sir.
Okay. So the time with which it can establish, remove any temperature gradient is much quicker than the time scale by which this temperature change is induced on the surface. So that's why it happens. So for those cases, we can think of this as temperature is uniform everywhere, but it's changing with time. Okay. So we can do a lumped capacitance. This is called lumped capacitance model. So for Bayer number much less than 1, we can do a lumped capacitance model. For Bayer number 1, in order of 1, of course Bayer number order of 1 means both are important. Conductive resistance and convective resistance are comparable. So we cannot neglect one with respect to another. So the analysis we did, that is needed here. If Bayer number is much greater than 1, so what will happen? Bayer number much greater than 1. What is the physical meaning of Bayer number much greater than 1?
Conductive more.
Yeah, conductive resistance is much higher than convective resistance. That means that the thermal conductivity of solid in this case is very low. So if you cool down the surface, it takes a whole lot of time for this heat to come to the place and make it uniform. It cannot. So if T ambient is the temperature, heat transfer coefficient is very high, so that very small temperature del T between this T ambient and T surface, very small temperature gradient can support the heat flux that is due to conduction. See, the surface, whatever heat is coming, so some part is going, so it's transient, so it's not exactly same, but you are removing heat from this and you are removing very efficiently. So whatever heat flux is coming, a small temperature gradient here is sufficient to take all the heat. So that means this TA and TS will be very little difference between these two. Alright, so we understand this, let's try to understand this clearly. That when Bayer number much greater than 1, for that case the conductive resistance is very high. So this the solid cannot establish uniform temperature. So they will always have a very strong temperature gradient inside. But the fluid in this time is very efficient in heat transfer. So that means the H is very high. H is very high means you think of H infinity, very high, like infinity. So already a very small temperature gradient will be able to support a reasonable heat flux. So understand this point clearly. These are very fundamental concepts. This will come back again and again in various shapes and sizes. So steady state, unsteady state, all cases, some heat, there is an interface, heat is coming from one side and going through another medium, another phase. Steady, whether it's steady state or unsteady state, something is coming and something is going. And if one side is more efficient in the other, gradient in that side will be always much lesser. So that is the basic thing. Okay. So in this case, what will happen? We can assume that T is approximately TA. Okay. So this boundary condition will change. So at zeta equals to 1, the boundary condition, if you see the definition of theta, theta is T minus TA divided by T0 minus TA. Alright, so just let me check because there are two definitions. Both are fraction of unaccomplished change, theta minus and 1 minus theta both are used. T minus TA, T0 minus TA, yes, exactly this is what we used. And at zeta equals to 1, because Ts is approximately TA, we can replace this boundary condition as theta equals to 0. Let me see if it is clear to you. Samira Yasmin. Samira Yasmin, turn on your video and tell me what you understand from this.
So there's a problem with the camera.
Huh?
So there's a problem with the camera.
I cannot, the voice is not coming clearly. Problem with what?
So the camera.
Camera, okay, no issue. Okay. But you understood clearly, right?
Yes, sir.
Okay. Tanay Vagane. Tanay Vagane. Yes, Jain.
Yes, sir.
Yes, sir. Turn on your camera.
Sir, I don't have web. My laptop.
Okay. Shubham Kumar. Shubham Kumar.
Yes, sir.
Yes, sir. Turn on your camera. What you said? Never heard of camera? Okay, very good. So you understood this clearly?
Yes, sir. Something.
Okay, so you can turn off your camera. So let us move ahead. So
Okay, sir.
So at Barrow number much greater than 1, that is greater than 100, so we can change the boundary condition because the conductive resistance is much higher than convective resistance. The temperature at the surface is almost same as that of ambient temperature. So the boundary condition becomes at zeta equals to 1, theta equals to 0. So that means solution is not dependent on Biot number. Exactly. Okay. Here it's dependent on Biot number. Here also it's independent of Biot number. Here also independent of Biot number. So now the question is that how we get the solution. So
We know that del theta is minus minus.
yeah, tell me.
So like
That
when guy is equal to 1, theta is equal to 0, right? So we had a previous boundary condition that theta by dou theta is equal to 2 minus di by theta.
No, voice was not very clear. So can you repeat the question? I don't know why net problem or something. I'm not getting anyone's voice very clearly. Can you repeat it? Or just type it in the chat box. I have another machine opened here. I can see the chat box.
Okay, so
yes.
Yeah, so we previously had one more condition. So now we just replace this condition. So we just replace this condition with the new one. Zeta equals to 1, del theta equals to 1. If theta equals to 0, so our differential equation got simplified. Exactly. So for bio number much greater than 1, our differential equation got simplified. Slightly simplified. Not a whole lot, but it's more importantly it become independent of bio number. Okay. Now the question is that how will you solve this equation? Any idea? So you know that solution, of course, that's why I'm asking. So it's not something new to you. I'm just trying to see if you remember that. Who will say? Awai sakta. You are aware, Girish?
Yes, sir.
Yes, sir. How will you solve this equation? Turn on your camera. How do you solve this equation?
By taking solving this equation at zeta equal to 1.
No. How you solve this equation? Zeta equals to 1 is only a particular point or line in this case. So this entire equation has to be solved. I want you to tell me some method that you already learned. So let me see others if they can remember. Who will say? Rahul Goldar? Adrija Roy?
Sir, we studied Fourier method, partial integration. I don't know.
So have you used separation of variable?
So that was ordinary.
No. There is only one variable in ordinary differential equation, only one independent variable. So you need not to separate variables. So variable separation is a typical method for partial differential equation. And also you get something called eigenvalue problem. So you have done the course on ODEPD, you know?
So we are doing it. We are studying.
Okay, this semester itself you are doing it, huh?
Yes, sir. Numerical for
No, not numerical. This is analytical method. Okay, so just since I thought you were familiar with this solution method, just give you an idea of how it may be solved. So we'll not spend much time on solution. If you understand, it's fine. If you don't understand, don't worry too much. We'll use the solution. We'll rather learn to use the solution than solving this equation. But I'm giving a brief idea of how to solve this equation. See, theta is a function of which two variables? Adrija, theta is a function of?
T.
Okay, zeta and t hat. We assume that theta can be written as a function which is solely function of zeta and a function that is solely a function of t hat. We assume that may not be the case. We may not be able to write it in this way. Okay, but we assume that, say we can write it in this way. Then our life becomes simplified. So partial theta, partial t hat equals to partial theta, partial t hat equals to we can write as f zeta dg dt hat. Similarly, we can write partial theta, partial zeta equals to g times df d zeta. And it's easier if we take the rectangular version of this equation. So rectangular coordinate system. So this is a spherical coordinate system. So in rectangular coordinate system, the equation will be simpler. Equation will be so d2 theta d zeta 2 equals to d tau. So in rectangular coordinate, this r square will not be there. So this is a simpler form. So in that case, you can write partial 2, these are partial. Partial 2 okay. Now substituting this, we get g times d2f d zeta 2 equals to f times d theta f times dg dt hat. Okay, so we now write this as 1 by f d2f d zeta 2 equals to 1 by g dg dt hat. So this is a function of zeta only, and this is a function of t hat only, and both are equal. So they has to be equal to a constant. So that we call as negative of lambda square. So that is the variable separation method. Now you solve this equation for f, solve this equation for g, and you get a solution like this, and then you write if theta equals to f times g equals to, you get basically, you see that g is exponential function, so g you get c3 e to the power minus lambda square t hat, and this is a second order equation, so you get sine cos term, you get c1 cos lambda zeta plus c2 sine lambda zeta. This is rectangular coordinate case. So now next you have to get these constants evaluated using the boundary condition in a typical case. There is nothing special about it. Only special thing is that because of involvement of sine and cos, you don't get unique values of these constants. You get and lambda especially. Lambda is not a unique value because of sine and cos. You get a periodic values of lambda. So this is called eigenvalue problem. So just keep this in mind. This is not something which you need, and this actually takes a lot of time that we don't want to spend here. But I'll show you the solution and how to use that solution. But this much information might be helpful for you to understand the solution. Okay? So, but I want you to understand at least what I said here. So if you have any question, we can discuss now regarding this solution of rectangular coordinate version of our equation using separation of variable.
I can't read it. You know that dot by dot is equal to 0. Dot theta by dot is equal to dot theta by cap is also equal to.
Well, this is some problem here because I'm not getting your voice clearly. I better let us discuss it in the chat box. Just type your question here. Variable separation method. So while that question is being typed, so let me just quickly go over the entire process. This is the partial differential equation. So we assume that this theta, which is actually a function of zeta and t hat, can be written as a product of a function which is a completely function of zeta and a function which is completely function of t hat. And then we substitute this assumption into this equation, and we get something like this. But the left hand side of this equation is function of zeta only, right hand side of this equation is function of t hat only, and they can be equal only when they are equal to a constant. And we assume that constant to be minus lambda square. Why such a strange value? Because otherwise it has to be a negative number, otherwise this g will blow with time. If you look at this function, it will be clear. So to make sure it's a negative value, we write it as minus of lambda square. Let me see what the question. if we know that d theta d zeta equals to 0 and thus d zeta d t hat equals to 0. No, we don't know d theta d zeta is 0 or not. These are all only at the boundary. Boundary. So we don't know d theta d zeta or anything we do not know. This is only on the boundary. Those will be used to evaluate constants, and some of those will go away. Okay, does that answer your question? So please type. Okay, good. Okay, so now let us look at the solution. Solution for the spherical case looks like this. Solution for the spherical case looks like this. Theta equals to summation n equals to 1 to infinity So this is the solution. And what is lambda n? Lambda n is the root of this equation. Okay. So this is the solution of the equation that we are talking about. We are talking about this equation, boundary conditions, Biot number limit. So Biot number much less than 1, we don't have to go for this solution. We will do something else. I'll show you that. Biot number 1 onwards, or rather, if we look at the limit, Biot number 0.02 onwards till 100, we have to use this solution. And beyond 100, actually we can use the solution for Biot number 100 for any Biot number above 100, because the solution is independent of Biot number. So now I want you to be clear about the solution and when to use this solution. Let me repeat again, Biot number much less than 1. You don't have to use this solution. A separate LAMP analysis I will show you, that has to be used. And what is Biot number much less than 1? Anything Biot number less than 0.02, less than equal to 0.02. Anything above 0.02, you have to use this solution. Biot number greater than 100, you can use the solution till Biot number 100. And why that is important, it will be clear. But look at the expression, and now let us think that for a given case, how will you solve this? So first, you have to compute Biot number, and then you have to compute lambda 1, lambda 2, lambda 3, lambda 4 by solving the equation 1 minus lambda n cot lambda n equals to Biot number. So you can see that solving this equation is not easy, because it's a transcendental equation. It's called, so numerical solution, okay, so this equation has to be solved numerically. So let us first discuss the strategy, then we'll discuss the how exactly we'll solve this. Okay. So we have to first calculate the bio number. Once we know the bio number, we get all the lambdas, and then the series is infinite series. Series is an infinite series. But this is a convergent series. That means that the terms are going smaller and smaller as you go from n equals to 1, 2, 3, 4. So you actually don't need to go beyond fourth term because this will be anyway very, very small. So for calculation of this, once you get all these lambda n's, you can put lambda 1, lambda 2 and you can calculate this series and get your solution for a given zeta and t hat. For any zeta and t hat, you can get the value of theta. So you can now choose another zeta and t hat, and since lambdas are known, so lambda all you have to do it, calculate it once for the given bio number, and then you can use the various zeta and t hat and get the solution. Some questions are there. So yeah, I think it's a good idea today to why we are using this equation to get lambda. Okay, so why we are using this equation to get lambda is a complicated thing. That you need some knowledge of the solution of partial differential equation using eigenvalue method. So I will inquire with your maths teacher whether it's coming in this semester, then we will not spend much time. Otherwise I will issue one notes on that, or you can look, I can issue a note for that. So let us not worry about at this point that why we get lambda from this equation, rather concentrate on how to get lambda from this equation. Okay. So this is, so let us look at this as kind of algorithm for getting the solution. So lambda has to be solved from this equation. How I will show you some way to do that, and you will not do that in exam or anywhere. You will do that. There is someone already has solved this. So there is a solution available in textbooks. So I will show you where you will find that in your textbook. So this equation, someone has solved for different bio number and provided you the values of lambda. Say suppose you get the values of lambda. So let us look at the values of lambda. So let me see. Let me open your textbook. Okay, can you see my screen?
Yes, sir.
Yes, sir.
Okay. So these are the coefficient. These are basically bio number. Someone has solved it. These are the this coefficient. Now the notation is slightly different here. Lambda, there is zeta 1 and c1. So to reconcile with our case, So these are the solutions. So you see that C1 is our case, what we have said, that's AN, the coefficients. So these are basically the coefficients, and whatever on the exponential, that is our lambda. Okay, so zeta is lambda our case. So these are the lambda for spherical geometry. These are various bio number. People have solved the this equation for this lambda. For our case, this is lambda. So you see that this solution is available till actually this is lambda 1. Okay, so you see that large number of lambdas will be there. So this is lambda 1. So they have called zeta 1. So similarly, you will find somewhere these values of lambda 2, lambda 3, lambda 4, etc. And if it's not there, we can use MATLAB. So let us think bio number. It's not yet ready. Say bio number equals to 1. And let us plot x equals to in space 0 to 10. So let us look at this equation. The equation is 1 minus, basically we are solving lambda. So let us, for a given bio number, let us first plot this as a function of lambda. Okay. So we can have bio number plus okay, so what I can do is that, so some of you are interested in the solution, we can work out good part of the solution after the class. Okay, so if you are interested, please stay beyond that after the class, I will show you the solution. It will take about 10-15 minutes it will take. Okay. For rest, if you are not interested in solution, is not needed, so just let us concentrate on how to solve this. So now I am trying to show you that how to get the roots of this equation, that is different lambda n. By plotting, so what I am trying to plot, bio number plus lambda n cot lambda n minus 1 equals to 0. So lambda n should be such that this value, this expression must be 0. So I am plotting it as f of lambda n. F of lambda n I am plotting in MATLAB. So f of lambda n for a given bio number. So for me x is lambda n. Okay. So x is this. So I have range it from 0 and then y equals to x cot x minus 1 plus bio number. X times of x minus 1 plus binomial. Okay. So this is x and y. Now let us plot x and y. Okay. Yeah, you see that this is periodic function. Now, of course, there is a cost, so it's a periodic function. And actually, there are discontinuities because it has added this, so the discontinuity is not shown. So it's better if we just plot it like. Yeah, you see that there is no value between this and this two. So discontinuity spark function, there may be a discontinuity. There is a discontinuity. Okay. And now we have to find the zeros. Where it touches zero, that are the roots of this. So let me put read on. Read on. Yeah, you see that somewhere near 4 there is a 0. These are lambda 1. There is one lambda 1 here. So possibly if we reduce the range, it will be clear. Yeah, you see that first one, first root came here. Oh, by the way, lambda is the positive root, so it need not to go in the negative direction. So it is symmetric, so it will come. So okay, so one root is something around 1.616. Okay, 1.616 is your first root. Let us see sphere bio number 1 I have taken, no? Bio number 1. Bio number 1. Yeah, this is the root. 1.57. Okay. And our MATLAB plot is showing is 1.61 or something. So that is because it's not accurate. So if you reduce the range and make this, you will be able to see. So the point is that you can see that you can get an approximate value of the root by plotting itself. Even you don't have to solve this equation. You can of course solve, but even you don't have to solve. You can plot itself, plot, and you can see the range or the number of roots. Okay. So I think we are reasonably good in looking at the number of roots. You change the bio number, the roots will change. But these are available in various handbooks and other places. So I think you get a reasonable confidence in how to get this lambda n. May not be in the exam. Exam we have something simpler. But for homework or somewhere, you know how to get the bio number. And that's why I didn't answer the question that some plot is missing or something. I think you will be able to solve it yourself. But I can take that question after the class. So this is now you know how to get this lambda n. And if you know the lambda n, you know how to get the rest of the solution. So any question on how to solve this, how to get the numerical value of the solution, that is numerical value of theta, if I supply you t hat and zeta. So the nature of question is like this. Time is given. I tell you at this time I want something. I know at these values of zeta I know I want this value of theta. You should be able to compute that using this expression. So if you have any question, if you don't feel confident, let me know. will we get same theta value for all roots of lambda? See how, okay, so first let me answer. Will we get the same theta value for all roots of lambda? See, these roots of lambda are different. So say if I take a particular example. Okay, next question, let me see. How many solutions of lambda do we need to approximately to get a reasonable solution? 4. If nothing is said in the question, you should take 4 lambda values. That means you go to this plot, get lambda 1, lambda 2, lambda 3 and lambda 4. Okay. Once you get lambda 1, lambda 2, lambda 3 and lambda 4, your theta is, so let us call it AN. Okay. Let us call it AN. So your theta will be A1 e to the power minus lambda 1 square t hat sine lambda 1 zeta plus A2 e to the power minus lambda 2 square t hat sine lambda 2 zeta plus A3 e to the power minus lambda 3 square t hat sine lambda 3 zeta plus A4 e to the power minus lambda 4 square t hat sine lambda 4 zeta. This is a 4th term. You can add more, but it will not be much. So, for example, so this term will give you 0.22321. This is a particular example. The next term will add only 0.00835. This term will add 0.00001. This term will add 0.0000001. So you understand that how quickly it converges. Okay, so let me see if this answers most of the questions. How many solutions of lambda do you need to approximate the reasonable solution? 4. Do we use plots every time to solve, or are they available in the books? Those are available in the handbooks. Could you explain the previous part once again? It's a bit confusing. Okay, let me go it over again. Okay, so let us start from the beginning. This is the equation. To get a value of theta for a given zeta and t hat, you need the solution. Solution is obtained by some method called separation of variable, eigenvalue problem. So these are mathematics stuff. We will not cover it here. But we know we will take the solution, and this is the solution. This is the solution. So this is the solution of the differential equation that we are talking about. And this solution has something called lambda n, because to get the solution, you know zeta and tau, at which people are asking you this thing, but we don't know lambda n. So lambda n has to be obtained by solving this equation. So this equation solution is dependent on Biot number. So take a simple plot, get fit the Biot number and get approximate values of 4 lambdas. Put these lambdas here, get A1 and these values. Okay. So you just add those up, you will get your theta. Never go beyond 4 terms, because you see that very quickly convert, this series is very quickly converging. Let me see. I can explain again if you still have some confusion, but you tell me the part which is more confusing. I can explain this again. Should we plot or take values from book? So if you get some reference from handbook where these lambda values are given at various bio numbers, go ahead and get those. If you do not get, you have to plot. Okay. Now more practical things. You can see that it's actually this first term itself gives you a very reasonable approximation. This first term itself is a reasonable approximate value of theta. So the table that I have shown you, that basically approximates theta as A1. Just let me check exact. So this is the first term approximation for sphere C1 exponential minus zeta square t hat. I said that t hat is actually Fourier number, so I wrote it as t hat. So it's basically t hat. So here the solution is C1 exponential minus zeta square Fourier number. So the approximate solution, they have put everything except the exponential term. So the A1, the C1 is actually takes this sign also. So this entire thing, they are packed inside C1. So the entire thing is packed as C1 e to the power minus lambda 1 square t hat. This is called theta 1 to tell you that this is actually first term approximation, not exact value of theta, but this is a good approximation when you have t hat greater than 0.2. This is a very good approximation, t hat greater than 0.2. So it's very easy to get this solution. You don't have to plot anything, you don't have to worry anything. All you have to do is to go to the table, find out your geometry, then read your bio number, get this zeta or lambda and this coefficient. So for bio number 1, if you want first term approximation, your solution is this is 1.2732 is the coefficient. E to the power, well, I need this sign. Well, it cannot be this thing because sign has zeta, so it cannot be packed. That's what you're wondering why they have packed that. Oh, there's a mid plane. Okay, so this is This cannot be packed here. Yeah. Yeah, sorry, this was not, this cannot be packed. It was wrong. So because it has this thing here, no? This X is here. X cannot be packed inside. So this cannot be packed. So A1 is C1. So this is time, and this is, we have this sign lambda 1 zeta divided by lambda 1 zeta. Okay. Yeah, now we are good. So this is the solution is 1.27, that was the coefficient, e to the power minus, and lambda 1, bio number 1 was 1.57 to the power minus 1.57 square t hat t hat sine 1.57 zeta 1.57 zeta. So this is the approximate solution. So you just put the value of t hat and zeta, you will get the value of theta at that location and that time. So 1.57 as I see the value, 1.57, yeah, 1.57, 1.27. Okay, so this is a little bit involved calculations, so just be sure that you understand how to get those values. Of course, we'll solve some examples. I don't know whether the example is in tutorial or not. So let us take 5 minutes quick break. It's 12 now. So we'll assemble 12:20 and then start solving a problem in this. So if you have question, you can feel free to ask in this break. Okay, so let us solve the problem so that things are clear. So you will need this table. I can put it on the screen. So the problem is so just do the simple problem. A solid sphere is cooling under bio number equals to 0.2. We want theta at zeta equals to 0.5 and t hat equals to 5. Okay. So first you have to make a plan. So no matter how simple the problem looks like, you should get a plan clear. Somil Bhailia?
Yes, sir.
Yes. What is your plan? What will you do? Others, please type your plan in the chat box. And Somil, you tell me what is your plan. What happened, Samir? Let me see any other people have any plan or not. Okay. Shomik Shatkar,
Yes, sir.
Yes, sir.
what is your plan?
Sir, we
Sir,
look
we
at the bio
bio
number
number
which is
which
more
is
than
more than
0.02.
0.02.
So
So
we'll
we
use
use
the
the
equation
equation
that
that
we
we
discussed just
discussed
right now.
right now.
Okay. So bio number is not much less than 1 because it's 0.2 and it's not also beyond 100.
Yes,
So
sir. And
the
the
partial
and
differential
the
equation
sphere.
is needed, right?
Yes.
So the partial differential equation solution will be needed. So that's the first part of plan. Okay. What is the next part of plan?
Sir, we are
So we are
looking
looking
at
at
it is a
it is a
sphere.
sphere.
Yeah, it's a
So
sphere. Okay. Next stage, what you have to decide? You have to decide whether you will be using the approximate solution or exact solution. So should you use approximate solution or should you use exact solution?
Approximate,
Why?
because
Because
theta is
theta
greater than
is
0.2.
0.2.
Yes. T hat is greater than 0.2. It's T hat equals to 5, way above actually. So you can happily use the approximate solution. So first plan is that Well, we need to use the solution of partial differential equation. We can use the approximate solution. What is the next part of the plan?
We have to
What?
find
Find the lambda.
point.
Yeah, for the given bio number, you have to find the coefficient and lambda. Now look at the table and tell me what is the coefficient and what is lambda.
Yeah. Satisfied. Like the by looking at the values of that.
Snehundu, your voice is breaking. So please type in the chat box.
0.599 C1 and 1.05 is xi. I mean lambda.
Lambda is 0.75. Huh?
Yes, sir.
Yes, lambda is 0.75 and coefficient is 1.0592. All right. So everyone got this, able to read those? It's a reading table, but see, in the exam you have to read this table. So just be sure that you can read it well. Anyone has any difficulty? How to decide whether to approximate value of theta by seeing value of t hat? T hat greater than 0.2, happily you can use approximate solution. The first approximate solution means this is the first term of the series. So t hat greater than 0.2. Okay. Okay. Good. So now tell me what is the value of theta? Get the value of theta and type it here. Okay. Varun Balakrishna, you are fine. Yeah, fine. Somik Sarkar, fine. Some more. Shanmukh, you have some zero missing. Just check carefully. Yeah? It's exponential minus lambda square. So this, just make sure that you have this lambda square. Yes. I wait for 4 more people to report values, then we'll move ahead. Rahul Nath, what is the value you are getting? Vaishnavi Malwani,
Yes.
what is the value you are getting?
So just
Okay. Okay. 3 more. Okay, 2 more. Good, 1 more. Done. Okay, so can you see my screen or you are still seeing the OneNote? Huh?
We are seeing
OneNote, okay. Okay, now you can see the next problem. Huh?
yes, sir.
Okay, good, go ahead. Solve this problem. First thing, make a schematic, make a plan, and then only go on solving. What is the first thing you have to do? You understand this is a transient conduction problem. So first thing what you have to do?
Find the
Huh?
find the Biot number.
Find the Biot number. Find the Biot number and then tell me. Then we move to the next part of the plan.
$47.5.
Okay, approximately 50. Okay. So I just give a minute for everyone to get the Biot number. In exam, if you complete the Biot number calculation in a 10 marks question, you get 2 marks for Biot number calculation and determining the regime in which you should work. So Biot number is not less than 0.01, neither greater than 100. So you again have to do that thing that you have to get. That is partial differential equation solution. Now the question is that is t hat. Now you have to, next point is to decide whether you have to use the approximate solution or exact solution. So how do you decide on that?
So we can't know beforehand because we don't know how long it will take to find it.
Exactly. Just let me share. Okay. Yes, Biot number. Many people are reporting Biot number. So I just, if you, as you get the Biot number, report the Biot number. Fatapat type karo so that I know that how many people are calculating Biot number properly. This looks trivial, but you know that many trivial things are not trivial in exam. So I want you to at least get the trivial things correct. If you can make the trivial things correct, there should not be any problem in getting reasonable marks in exam. So that's a thumb rule. Okay. So there is no way because the time is being asked. So time is not given. So because time is asked, time is not given, you do not know whether t hat is greater than 0.2 or not. So what is a wise thing to do?
Like we use full solution. It will not use
Okay. So maybe the wiser thing is to do is the full solution. But the engineer's way to do is use the approximate solution first, and then from there get the t hat. And if t hat is smaller than 0.2, then try to use the big solution. So let us be engineer and let us try using the approximate solution first. So let us hope that it will work. May not be. So we are not always correct. But this is the typical style for engineers. Use the approximate thing first and then check whether the assumption was correct or not. So we assume that t hat will be greater than 0.2. Okay. So approximate solution. So what are given? So first to try to find out what are given in this case. So Biot number you have calculated to be 47 point something. So now look at the chart and get what is your C1 and what is the coefficient and what is lambda. You can approximate it to be 50, For this class you can take, otherwise you can take linear interpolation. Because we are solving a problem in class, take Biot number to be 50. Fatapat report the lambda and coefficient. Don't interpolate, take 50 and fatafat see the table and report that. Even make more approximation, take coefficient 2 lambda 3, right? Coefficient 2 and lambda 3. That is the approximate values. Let me check. 50 pe lambda 3 coefficient 2. Coefficient 2 lambda 3. Okay. Good. So coefficient 2 lambda 3. And now from that, tell me what is the value of t hat. What is the value of zeta? And what is the value of theta? Those are given, right? The location is given. Location is given and theta is also given. So get those values and type those fatafat in the chat box.
These
Type करो उसमें बंधु, I cannot hear clearly. Okay. So the plan is that, now let us zero on the plan. Plan is that they are asked that an ordinary egg may be approximately 5 centimeter diameter sphere. The egg was initially at 5 degrees centigrade. So T0 is given and is dropped to boiling water at 95 degrees centigrade. So T ambient is given. Considering the convective heat transfer coefficient 1200 watt per meter square Kelvin, determine how long will it take the center of the egg to reach 70 degrees centigrade, right? So the R coordinate are equals to 0. That means the interest where you have to find out the temperature, that is R equals to 0, that means zeta equals to 0. And they are asked that what will be the time when the center of the egg reaches 70 degrees centigrade. So at that location, the temperature is also given. So T is given, TA given, T ambient given. So we get theta. So basically theta and zeta both are given and time is being asked. So we can look at the approximate solution and theta, zeta and time. So we see that the entire equation, only the t hat is the unknown. So you have to solve it for t hat. So that is the plan. And the value of theta is 0.27, yes, correct, 2778. Yes, so theta is not known, now known, and zeta is 0. So now only report the value of t hat. Yeah, I started seeing the values now itself. I want more people to complete this problem and report the value of t hat. Yeah, take your time and do it carefully and understand these steps. Yes, correct. More t hat. Yeah. I wait for 4 more t hats. Okay. I have good number of T hats here. So now next is the T. Yes, approximation is correct. And even if it's slightly less than 0.2, it's not worth going the hassle. You see that getting T hat from a series is not that easy because it's a exponential, so it's a lot more hazardous, lot more difficult. I'll not say hazardous, lot more difficult. So it was possibly not worth even it's slightly less than 0.2. Okay, now get T. Take density as density of water, Cp as Cp of water, get alpha and get the dimension is given, so radius is known, get T. What is Cp? Cp is the Cp of water. And what is Cp of water? I will not tell you. And we put the T in minutes. Density is density of water, Cp is Cp of water. Yes. Yes, correct. Two values, some more. Now this problem is an ideal example where you need to look back sometime. So a little mistake here and there may give you some weird values. So you know that how much it takes for an egg to boil. It's not 5 days, it's not 0.026 seconds. So always if you get reasonable values, so you're fine. Yeah. 1, 2, 3, 4, 5. 5 more. Yes, we assume that the material of egg has property of that of water. It's actually water protein solution, so I have taken it same as water. Maybe slightly different, but it's okay. Okay. One more. Okay, done. So that's it for today. So anything you have to ask, any clarification of the entire process. So make sure before you leave today that you understood how to solve transient conduction problems. Using the approximate solutions, first term series. So entire thing is here. And if you're interested in the solution, how the solution came, so we can make the solution. We can do the solution a little bit in detail. Okay, now let us see the figure, which figure we are talking about, whether that is needed anymore or not. So let me share my screen. You can see my screen now? Huh?
Yes, sir.
Okay. So now we have to go to homework. So how can I go to the files? Or any one of you can want to share screen and show me that which problem exactly is bothering us. Fine. It's homework 2, right? No, homework 1, problem 2. Homework 1, problem 2. Two by 4 woodsters have actual dimensions and thermal conductivity. Okay, I understand now. Okay, so this I have to supply. Yeah, I understand. I thought these are Hessler chart or something which I avoided later. So it's not that, something else. Anything else? Any other problem with the homeworks? Is problem 2 homework 1, no? Okay, so files. I'm uploading the figure. Just make sure that files upload. Okay, I've uploaded the file. So just make sure that you can see that. Huh? So some of you please check and see whether you can see that file.
Yes, sir.
Okay, good. So that problem is solved. Okay, I think we now overshoot the time. So how many of you want to stay for another 10 minutes and see that solution? I can do that. I have no problem. So those of you want to see the solution of this equation, stay, or if you don't want to want the solution, then you can leave. So depending on so whoever stays, I will show the solution. Okay, we still have 10 people, so let us start. So by assuming that these 10 people are at least interested in the solution, so let us go here. So it's easier to work the solution for the rectangular coordinate case. And if you see the rectangular coordinate transient problem, this is the transient equation. Del T is alpha del T2 del H2. No R square kind of things. And this thing boiled down to be so dimensionless equation del 2 theta del x2 equals to t hat. Okay, the initial condition is theta equals to 1 at t hat equals to 0 for all x, and boundary condition at x equals to 0 and at x equals to 1. These are two boundaries. X equals to 0, x equal to 1. X equals to 0 condition is that del theta del x equals to 0, and here the condition is that del theta del x equals to minus bio number times theta. So this is the equation, and in a separation of variable, let me check. Oh, still 8 people are here. Great. So separation of variable is that we assume theta is a function of f, which is a function of x, and g, which is a function of t hat. This is a pure function of t hat, pure function of x. So we substitute it here. We get del 2 theta del x2 equals to g, which is a function of t hat, d2 fx dx2. We get del theta del t hat equals to f function of x dg dt. So once we substitute it here,
Can
we
we
get,
always, sir, can we always theta as explicit function of t hat? Implicit can also like they are separate those two.
so better you just give me a call at this number. The voice is not clear. Okay. What if theta is an implicit function of x and t hat? If theta is an implicit function of x and t hat, we cannot do this. Okay. This assumes that this kind of separation is possible. If that kind of separation is not possible, we cannot do this. So this is under a certain assumption. Okay. And how this dimensionless equation came? Same way, just instead of spherical coordinate, we did this in rectangular coordinate. We have to take that equation that we derived at the beginning of the class and then do the same non-dimensionless, and we will get this equation and dimension and the boundary conditions. Okay, Samira Yasmin, your question is answered. Okay, all right. So now once we substitute this, we get G so we can write it as okay. So now this side is till this point you are clear, no?
Yes.
Okay. So now see this left hand side is a function of only x. Right hand side is a function of only t hat. So a function of x cannot be equal to function of t hat unless both are constant. Okay. So this has to be a constant. Now the question is that can we say anything more about this constant? Can it be a positive constant? It cannot be a positive constant because if you see that, if you say it's a positive constant, then we have dg over g equals to that constant, say lambda dt. If you integrate ln g equals to lambda t plus c, so g equals to e to the power lambda t plus e to the power c. So you see that as t goes to infinity, this goes infinity. So that is not possible. So that's why this constant has to be a negative number. So to make sure that it's always negative irrespective of whatever we do, we say this is minus lambda square. Lambda square is always positive. So no matter what lambda is, lambda square is always positive. So minus lambda square is always negative. Okay. So now if we solve it, we get same thing, that g equals to c3 e to the power minus lambda square t, and f equals to, so we can write f equals to c1 e to the power lambda x plus c2. Well, lambda is, so this is lambda is this is positive, so it will be complex roots. So it will be sine cos. So it will be, so what we have? We have d2f dx2 plus lambda square f equals to 0. So we get d square equals to minus lambda square, d equals to plus minus lambda I. So we get the sine cos solution. So f equals to c1 cos lambda x plus c2 sine lambda x. So our solution theta equals to c3 e to the power minus lambda square t, c1 cos lambda x plus c2 sine lambda x. So actually these two constants can be merged into a and b. So you can write theta equals to, you can write that e to the power minus lambda square t A cos lambda x plus B sin lambda x. So this is our solution. Now we have to get the constants evaluated. So constant evaluated. So we know that at x equals to 0, d theta dx equals to 0. So d theta dx equals to e to the power minus lambda square t, lambda square t, a lambda minus sin lambda x plus b lambda cos lambda x. So at x equals to 0, so this goes to 0 and this has to be 0. So that means b must be 0. So the solution now becomes theta equals to e to the power minus lambda square t a cos lambda x. Okay. So this is now reduced solution. You see that we are gradually approaching what we had. Now we'll use this boundary condition. At x equals to 1, d theta dx. Now d theta dx equals to e to the power minus lambda square t a negative again lambda sin lambda x. Okay, so this is minus bio number times theta equals to negative of e to the power minus lambda square t, actually t hat, okay, a lambda sin lambda x. I need to write it clearly. So this boundary condition becomes, so let me write it here clearly. So d theta dx is negative of Biot number times theta. This becomes negative e to the power minus lambda square t a lambda sin lambda x. Okay. Now let me also replace theta here, minus bio number times theta is e to the power minus lambda square t a cos lambda x equals to minus e to the power minus lambda square t a lambda sin lambda x. So you see that we use this boundary condition for evaluating A, but unfortunately we could not evaluate A from this. But we could evaluate lambda, because lambda is also not known to us. So lambda is also not known to us, so it serves some purpose. So these actually cancels, these cancels. So that gives us lambda tan lambda x, x equals to 1, so this x will not be here. So lambda tan lambda equals to bio number. Okay. So now this is a periodic function. So what is the, if you solve this, you don't get a single value of lambda. You get a set of lambdas. So you are aware of superposition principle. So all these solutions has to be superposed. So we say now this theta is e to the power minus lambda n square t hat a n cos lambda n x. That is my solution, and all these solutions are superposed, n equals to 1 to infinity. Till this point you are fine? Let me see how many are still there. 7 people are still here, okay. So everyone is fine till this point? Superposition? So that's how actually you get this series. So let me see. Someone is asking something. Yes, sir. Good. Now you see that this Fourier series, you studied Fourier series, no? You studied Fourier series in Maths 1 or Maths 2 or somewhere?
Yes, sir. Yes, sir. It was.
See, Fourier series, this is, so when the Fourier series is taught in the first year or second year students, they think that kahan se aaya, why this strange thing comes. But actually it comes from this solution. So the Fourier, Joseph Fourier, who actually Fourier's law and all these things, he got this series, he used this series for solution of this, evaluating these constants. So this Fourier series or this series, those are basically kind of orthogonal properties of polynomial, orthogonal polynomials. You heard the term orthogonal polynomial?
Don't remember.
Okay, all right. So it's orthogonal. What is the meaning of the term orthogonal? Perpendicular. So, like if you have the three-dimensional space or any two-dimensional space, your x and y coordinate both are those are orthogonal to each other, right?
Yes, sir. Yes, sir.
So any point in this two-dimensional space can be expressed in terms of these two basis coordinate or basis of these two coordinates. So these are the orthogonal coordinates. Similarly, you can express any function in terms of a set of orthogonal functions. So multiplied by multiplication of those orthogonal functions by certain constants, you get any function represented by those. Those are orthogonal properties. There are a number of orthogonal properties that are there. So, so you see that how this series comes. Now you have to evaluate this constant. So our attempt to evaluate A failed. Rather, it gave us how to get this lambda, but we still has this unknown n here. So we now use the initial condition. We haven't used that yet. So initial condition is that at t equals to 0, theta equals to 1. So that says that 1 equals to summation of n equals to 1 to infinity a n cos lambda n x. So this equation will be used for getting the value of a n. And there we use the Fourier series properties. We multiply left hand side by cos lambda m x equals to summation n equals to 1 to infinity a n cos lambda n x cos lambda mx, and then integrate it from 0 to 1 dx. Integrate it from 0 to 1 dx. So that will give us integration of 0 to 1 cos. Okay, so This has some special properties. So these are orthogonal polynomial, orthogonal functions. These are not polynomial, these are trigonometric functions. But these are orthogonal functions. And this is non-zero only when m equals to n. Okay. So except all other values, if you integrate this, you will find that this comes to 0. You can check it yourself. So for m not equals to n, this will come to 0. So only when m equals to n, then only this right hand side has non-zero value. So setting m equals to n, cos lambda n x dx equals to an. There is no more sum because this is only one term remains. Some certain value, say n equals to m. So let us keep it n. So a value of n equals to m only, this becomes non-zero. So am equals am integration 0 to 1 cos lambda m x square dx. That gives us the value of am. The value of am equals to integral 0 to 1 cos, okay, this is m, lambda m x divided by integral 0 to 1 cos square lambda m x dx. Okay, so this will come to be 4 sin lambda m divided 2 lambda m plus sin 2 lambda m. So you can do all steps except, so I only little bit magic I have shown here saying that except m equals to n, all other will be 0, some orthogonal properties. So this is how you get the coefficient am. So this is for rectangular coordinate system. Spherical coordinate system, you need you get another function. For cylindrical, you get in terms of Bessel function. So I think ODEPD, there was a course on ODEPD. I don't know whether they teach this or not. Separation of variable, eigenvalue problem. So at least those multiple students will do that in this advanced mathematics. But I thought this is a part of maths course as well. So now your task is to look at this portion. So just using initial condition, we got this equation. I think this we are fine. So this equation you can get. Now multiply both sides by cos lambda mx and integrate from 0 to 1. This is an operation. You know that various operations we can do. Now this orthogonality property, you can check yourself that cos lambda n times cos lambda mx integrate from 0 to 1. It is non-zero only when m equals to n. So in the entire series, only one term survives. That is the am. So am 0 to 1. So this is non-zero. So that's how we get am. Am equals to 0 to 1 cos, and then this is a little bit of, you can just do this. You will get this. So this you can readily see that integral of cos is sine. So just denominator you have to little bit make cos square theta to in terms of sine 2 theta, and you will get that as well. Okay. So happy?
Yes. Thanks.
Okay, I'm still there till 2 o'clock. So if you have question, I can still answer. So it's not a problem. You don't have, you are okay. You saw, you understood that how this solution works. You can also leave, no problem. Mm-hmm.